Okay, so I'm back, Shane Snyder from Argonne, to talk about how to understand and tune HPC IO performance. So this is general talk on those topics, but again, it's kind of also like a deeper dive into the Darshan concepts we covered earlier, and also some of the IO library stuff we've heard of. So hopefully it starts to help you put things together. But yeah, the background is that you guys have heard a lot of different presentations today, and they've kind of evidenced that the HPC IO landscape is pretty deep and vast. There's a lot of different layers, as I've got depicted over here to the right. You start off with your application, and then you work through some data abstraction. So at the high level, you've got like HDF5 and PNet CDF, which we've heard about. Then you've got transformations, which we've heard about via MPIO. And then we've got the parallel file system underneath that, which could be things like Lustre or GPFS and so on. And at the very bottom, you have IO hardware. So hard disk, SSDs, NVM, all different things we've heard about. So you can see how this can get super complex. And as a user, that can be pretty daunting, obviously, if you're thinking about how to first understand what's going on, and second, how to tune things to get better behavior, better performance out of your application. So part of the problem is not only the complexity, but these high-level data models that users really like to use for convenience, like HDF5. It's great for storing scientific data and kind of divorcing you from the lower level storage details. But whenever it comes time to really think about tuning, it does kind of hide some of the lower level details, where you really kind of start getting, or where you can really kind of orchestrate better performance. So again, this is really complicated, so don't feel like alone if you feel that way. But hopefully in this talk, we'll be able to help navigate it a little bit and come up with observations and actionable tuning decisions from this. So we've already heard about Darshan a good bit, but just a quick recap. It's just a powerful IO characterization tool that can help users better understand and tune their workloads. Darshan can provide a lot of helpful stats across all these different layers of the IO stack, which again are really critical to helping understand application biobehavior. So here I'll just kind of quickly walk through the types of stats and information that we capture from different API levels. I don't think I really got a great chance to do that in the intro to Darshan talk, as it's a little lower level details, but this should give you some ideas about what sort of information we're capturing, and then we'll use that information for some use cases to walk through. So we'll start with HDF5. So HDF5 support in Darshan was added sometime in the last couple of years. So starting with Darshan version 3.2.0. I think Cori and Theta both have this version of Darshan available. Only Cori has an HDF5 enabled version of Darshan. It's something additional you have to configure and build. So it might be easier in a lot of cases to build this yourself if you get more comfortable. But the idea is eventually we'll be able to have HDF5 enabled versions of Darshan on all these systems. So we'll keep working towards that. But as far as what's available for HDF5, we instrument two different APIs there. So there's a file API inside of HDF5 that's actually pretty thin. There's not really a whole lot of interest to instrument from there. It's mostly just creating or opening files and closing them. But we do capture, the total number of times a file was opened or created, how many times it was flushed. We capture whether the file was configured with to use MPIO. There's a property list you can pass to tell HDF5 to use MPIO. So we capture whether users are trying to use that. And we also capture some metadata timing, so how much time was spent opening and things like that. The more interesting HDF5 API from a IO performance perspective is definitely the dataset API. So this is where users describe their datasets and issue reads and writes to them, basically. So this is where a lot of the IO obviously happens. So in this interface, we're capturing operation counts, so like data operation counts like read and write, metadata operations like open and flush, things like that. We also capture total IO volumes to individual data sets. so how much data was read or written to a particular data set. We capture some common access info. So whenever users issue read-or-write operations to data sets, how large are they in general? If they're using like HDF5 hyperslabs, like what are the dimensions that are accessed, things like that. We also capture chunking parameters, the more details about the data space that is associated with the data set. So how many dimensions it has, how many total points, just to give a feel for how large the data set is. And then here we also capture whether MPIO collectives were used. So HDF5 can use MPIO independent operations, or it can use collective, and that's something users can control. And we capture what the users are trying to do there. And again, we have more metadata and data timing information. In the MPIO layer, there's more operation counts, obviously. So read and write, sync are the big ones for data. For metadata, it's mostly just open. We capture whether users are using collective or independent operations. Again, there's two different classes of IO operations in MPIO, and we're just trying to capture for each file, which types of operations are being used. Also, total IO volumes, obviously, so total amount of bytes read or written to a file in this case, as opposed to data sets for HDF5. And then more access size information. So not only like the most commonly used access sizes for an application, but also just a histogram, which I showed this morning, showing you like the complete distribution of access sizes issued. And then there's more data and metadata timing. POSIX is kind of similar in terms of what it captures compared to MPIO. So again, more read, write, sync. On the metadata side, there's a little bit more interesting stuff happening here. So not only opens, as you would expect for files, but also seeks. So moving the file pointer around to different spots in the file looking for data, and also stat, which is just like a general operation to get some basic details about a file that's used pretty commonly. Moving quickly through these, but stuff we've already considered mostly: total IO volumes, so total bytes read or written, common access size information. We also capture information on strides. A stride is basically the difference in offsets between consecutive accesses. So things tend to perform better whenever files are accessed, kind of sequentially. So like a stride of 0, the next operation falls directly after the one before it. So if you see strides that are large, or if you see seeking backwards in the file or stuff like that, something that might be useful to know about, and that's something that we do capture. We capture file alignment information, which is important, as we'll see in an example here in a little bit. We also capture more data and metadata timing at this lowest layer of the software stack. One additional thing we do capture is information on the Lustre parallel file system in particular. That's the only one we capture additional details on. But we capture the stripe size and stripe width that are being used, and we also capture, if it's useful, a list of OSTs that serve a particular file. So next, we'll just kind of walk through some examples that see how we can use Darshan for different practical use cases that are, I think, helpful for demonstrating some best practices that I've observed over the years in HPC IO. So we'll start at the bottom and work our way up. So we'll start with tuning the parallel file system. And the goal here is to basically just ensure that the storage resources, that you're allocating storage resources that basically match your application's IO needs. So I think we've heard a bit about it today, but for parallel file systems like Lustre, they do have some parameters or settings that users can directly control. In this case, we're talking specifically file striping parameters. What size chunks or files broken up to, that's like a stripe size, and a stripe width, which is how many file servers a file is striped over. So it gives you information on how a file is broken down and how it's distributed across storage servers. Just kind of a broad takeaway from here is just that the bad news is mostly just that users do probably have to have some sort of knowledge of the file system to get really good IO performance. I think we all kind of just would prefer to not have to concern ourselves with these sorts of details and just automatically just get the best performance out of the box. But that's just not always the way things work. So the other side of the coin is that, the good news is that there often is a lot of room for improvement if you're able to thoughtfully think about a lot of this stuff. So file systems aren't perfect. Basically every layer of the IO stack we've covered isn't perfect. There's definitely probably some room for improvement, particularly for workloads that they might struggle with by default. There's always going to be something that you might be able to do as a user to get better performance. We'll cover some of those examples here. So just as a simple starting point, we'll just consider a simple simulation application here, where I've just got 4 processes depicted on the left, and they're each responsible for writing their own independent chunk of simulation data. Now, this simulation data is really large-scale data that's generated or processed on the supercomputers. So it's a really large chunk of data. Maybe definitely way more in gigabytes, maybe like exabytes or something like that. Or sorry, not exabytes, like terabytes or something like that. And the idea is, without much configuration, you might get yourself in a situation where all 4 of these application processes are writing to a single server. Maybe that's not bad, but like maybe you scale this up to 16,000 processes or something like that, and they're all hammering on the same file server. That's not an ideal workload, as you can imagine. So what you would actually prefer in a case like this is to configure the storage system so that you have storage resources that are better matched to your application. So in this case, you would prefer to load balance each process's large data contribution to different storage servers, as you see here, and that eliminates the hotspot of a single server, and it gives you a better load balance, so you can take advantage of these storage resources in aggregate instead of just counting on a single server. Another example that you commonly see is something not a large data set, so maybe like a simulation config file or something like that all the processes need to read before they can start their simulation. So this is much smaller. You're talking probably on the order of like kilobytes or something like that. And in this case, again, every process needs it. So what you could do is just store this all on a single storage server. There's no real benefit to breaking this up and spreading out across multiple servers. It just creates complexity for retrieving the information, and it's all really small. It's easy to all host at one spot. There's actually a secondary optimization here that you frequently see, though, and that again, if you can imagine 16,000 processes or something like that, all reaching out to a single storage server to get like a really tiny piece of information, it creates a kind of a big bottleneck. So what you could do instead is try and alleviate that storage contention and just have a single simulation client read in the data and then use the high speed, less contentious compute node network to distribute that to other application processes. And that'll generally get you a lot better storage performance too, as you're not, again, overloading every single application process onto a single storage server. So yeah, well, one thing to keep in mind, I've hinted at this, is just be aware of what file system settings are available, and don't assume that they're always going to give you the best behavior by default, because you could be surprised by what you find. So one thing worth mentioning along these lines is that both ALCF Theta and Nurse Cori both default to a Lustre stripe width of 1. So what that means is by default, whenever you create a file on these file systems, it's going to be striped across a single server, which is what we saw, in a previous example, not necessarily being the greatest. And I've got some actual concrete numbers here to hammer that home, basically. But I've essentially just created a really simple test program that does, it's 10 processes over 10 nodes on Cori, doing a really simple POSIX IO workload to a shared file on the Lustre scratch volume there. And you can see here, snips some information from the Darshan job summary and also some parser output to go through. But the runtime was 6 seconds, so it's not, it's not very intensive or anything. Just really simple toy example. But you can see it transferred a gig of data at 200 megabytes per second. If we peek at the luster counters that come through the Darshan log, you can see the stripe size is set at a megabyte, which is the default, and also the luster stripe width is set to 1, which is also the default. So all of the data is going to a single server, in this case storage ID number 100. If you use this command called lfs set stripe, it lets you basically change the striping parameters for a file. So I basically went back and reran this simple benchmark, but changed the striping factor to 10. That's what this -c 10 switch does. And test file, it's the file in question. So now we've configured it to use 10 storage servers instead of 1. You can see here the runtime was cut in half for this simple example. And we see like around a 200% performance boost just by this one little simple configuration change. And you can see in the Darshan parser output that now we see a stripe width of 10, and you can see all the different storage IDs that are helping here in case that information is ever useful. But this is, again, just a really small scale example, but it gives you an idea of how a simple optimization like this, just being thoughtful about it, can get you some pretty serious performance gains. So we'll move on or I guess move up to the next layer, which would be the POSIX layer of the IO stack. So this is the, kind of the no frills IO API. There's no, notion of collective IO or things like that, as we've already heard today. It's just kind of like a direct access to the storage systems from this layer. One thing that is important here that users aren't necessarily always aware of is file system alignment whenever you're creating IO accesses to a file. So IO or file systems tend to have this notion of blocks, and it stores data in blocks. And if you start accessing data that kind of goes across block boundaries, then you get into some, I guess, unoptimal access patterns for the storage system protocol. So a lot of times users in IO middleware and libraries and things like that will try to avoid that and just ensure that their IO is well aligned to these file system block boundaries to get the best performance. So as a simple example here, again, just a really like toy example, just two processes accessing a single file. The big black boxes are basically the file system blocks, and the two colors, blue and red, are what portions of the file are being accessed by each process. You can see here that the alignment's way off, so each process is accessing half of its data from one block and half from another. And you can see how that translates to the bottom, the storage system backend, with each process having to interact with both of the storage servers to get their tiny blocks back. So that can really introduce some inefficiencies in storage protocols that people generally would like to avoid. So in this case, we would prefer that clients actually issue operations that are aligned on those block boundaries as we show here. And in that case, all of their data is basically mapped to a single server, and it really simplifies the process of reading or writing that data. So just some more numbers we can walk through to again, hammer this home. I think, yeah, this is the same exact example as earlier. So we've used the stripe width of 10 here rather than a stripe width of 1 to start off with somewhat reasonable performance. But then we're going to compare what the performance looks like for unaligned versus aligned IO. So again, we transferred a gig of data across 10 processes at about 310 megabytes per second. And I pulled some of the Darshan DXT tracing information I mentioned this morning. So this is a full trace of every operation that's issued. And you can see here, ranks 0, 1, 2, 3, they're all doing writes. All of the writes are 1 megabyte in size. But you can see on the offsets how they're offset by a half megabyte. So the first one's at a half megabyte, process 1 writes at 1.5 megabytes. So it's basically the same exact scenario we considered visually on the previous slide. Each access is going to basically talk to two different stripes of the file. And can see what happens in the aligned case. So I changed it so the offsets are aligned on the block boundaries or the stripe boundaries for luster, and you can see that on this offset field, they're all well aligned. And you can see in this case that we do again get it's not as drastic as the stripe parameters that we considered earlier, the performance boost there, but we still got like roughly like 25 to 30% performance boost just ensuring that we're aligned. So moving up, we'll go straight to the HDF5 layer, which is about as high up as you can get before the application. And remember that you guys have heard a little bit about chunking today. So this is basically a mechanism that allows users to partition how their data sets are serialized into a file. So let's see, yeah, let me click through to the figure. So one thing users can do is, by default in this figure here, you can see the HDF5 will store data set contiguously row by row in a file. Now this is fine if maybe this is exactly how you intend to get the data back out of the data set. But if your access patterns don't follow this, then you can get into some inefficient I/O basically. So yeah, so what you want to do is, or actually just to kind of illustrate this on the left side here we have a column-based access pattern, and you can see what would happen if a user had to access a column instead of a row. So you'd have to for the blue color is one process, and you would see it would read this very first block in the file, then it had to skip through 3 blocks and then read another. And it would have to do all of this. It leads to basically a lot of inefficient reading and reorganizing of the data. Similarly, to the right side of that is another common access pattern where it's block-based. So in this case, maybe the blue data wants to read this first block in the data set. Again, it would only be able to read the first 2 elements, then it'd have to do a seek back to the third and fourth, and it just really kind of creates a inefficient workload. Let's see. So I have some results from a simple example that uses a block-based decomposition like we've shown there, and we can kind of work through different HDF5 optimizations and see what kind of impact they have on observed performance. So again, this is 256 process, 16 nodes on Cori, and each process has exclusive access to a block of the data set. I think these blocks are 2K by 2K, which comes out to 32 megs per process for a total of 8 gigabytes. And so like what I was getting at with no chunking, each process has to issue many smaller non-contiguous IO requests, and that gives you lower performance. So again, in this figure, the solid arrows represent like contiguous reads or writes, and the dashed lines represent seeks that happen to move the file pointer to the next appropriate spot. So you can see read a small chunk, then seek, read a small chunk, then seek, and you can kind of see how that can lead to a little bit more inefficiency. So some Darshan job summary output I've snipped to kind of help drive this home. But again, this is 256 processes. It took 143 seconds to run this benchmark. It's 8 gigs worth of data, and it did so at like 58 megabytes per second, which is pretty slow. You can see kind of just working through some of the Darshan graphs we covered earlier today, but you can see in this operation counts graph, there's a ton of POSIX and MPIO independent operations issued, about 500,000 of them. If you look at this common access sizes table next to it, you can see that there's like 520,000 accesses of 16 kilobytes. Those are pretty small accesses. It could be worse, obviously, but those are pretty small from what you would generally try to do for a parallel file system to get the best performance. And in this case, you can see that the performance is obviously really low for this data set. Next, we'll consider what happens when we apply chunking. So with chunking applied, we no longer have to have this seek for each process. So the blue process here would read all 4 of these chunks contiguously from the file. There's no seeking that needs to happen. And for the Darshan results for this one, you can see that the number of operations issued is way lower. So where we were looking at like what 500,000 previously, the number of operations issued here for the common access size is 256, which matches our number of processes exactly. So that kind of matches what we went over. Each process is able to read their whole block in one single access size instead of many, like we saw in the previous non-chunked example. And we can see here that that the performance almost 3x'd compared to chunking in the small example. So you can see just a simple optimization like that, where you're really trying to organize the data in the file in a way that's conducive to how it's actually accessed by the application, can really buy you some big performance improvements. An alternative optimization to chunking that I've considered here is collective I/O, which we've heard about plenty today. It's another way that you can kind of improve efficiency of workloads like this, where individual access patterns might not be best for how data is organized in file. So in this case, we're going to rely on MPIO's collective buffering algorithm to give us really large contiguous storage accesses. And secondarily, another improvement that algorithm does is it limits the number of clients that interact with the storage system. So in this case, it's a little more subtle what's happening here, but with collective I/O enabled, there's designated processes that are aggregator processes, and those perform all the I/O on behalf of non-aggregator processes, and they just communicate with each the non-aggregators using MPI. So you can imagine in this example over here that the blue process is responsible both for its data and the green process's data, so it's able to read all of that data contiguously, or write it in this case, and then use MPI collective communication to share that information with the corresponding non-aggregator processes, and similarly for the red and yellow processes. So you can see it gives you better performance ideally by allowing you to keep making large contiguous accesses, but it's not necessarily relying on chunking. It's a little bit different than what we saw before. So some Darshan results from here. You can see that we are able to transfer the 8 gigs here at 270 megabytes per second. So that's like 4.5x over the original no chunking, and 1.5x over the chunking. So this is definitely the most performant. What's a little interesting about it is that in this case, there's 8,000 of the common access sizes issued here. Maybe it's not intuitive that more write operations in this case actually gives you less performance than the previous chunking case where everyone writes everything in one go. This is just kind of the magic of the MPIO collective algorithm. It's just really well optimized for things like luster. It knows how to construct the file system accesses to get the best performance. And in this case, you can see that the common access size is 1 megabyte, which is exactly what a luster stripe is. So it has a very luster stripe aware collective I/O algorithm that's able to get better performance even than our chunking optimization. Just a couple of other graphs I have related to HDF5 analysis. The Darshan job summary stuff we've covered so far today, it has a lot of really helpful graphs, but one thing it does not have is HDF5 information. If you're using an HDF5 enabled version of Darshan, that's something that we are definitely working on and want to have something available for users soon there, because we know users get a lot of bang for their buck with this job summary tool. It's just that it doesn't currently have any of the HDF5 data. So I put together using Python just some simple analysis of some HDF5 data that I had laying around, just to give you an idea of what kind of analysis you could do with it. So this particular example is Maxio, which is a pretty representative I/O benchmark for HPC. It does 3D particle meshes, and it has an HDF5 enabled backend, which makes it attractive for kind of testing out this HDF5 enabled version of Darshan. but I was able to do a pretty small scale 60 process 5 node example, writing to a single shared file, about a gigabyte of data using HDF5, and just wanted to compare performance of collective and independent IO configurations. And I've got the timing of each of those kind of stacked on top of each other here for independent and collective configurations of this workload. So you can see the independent is much slower. It's got basically a 30 megabyte per second bandwidth, whereas the collective version has nearly 300. So it's basically like an order of magnitude difference between the two. What's interesting is if you kind of compare the contributions of each of the IO APIs to the timing in each case. So on the left side, starting there, you can see that POSIX IO completely dominates the runtime there. The reason for this is just that this workload isn't decomposed into really efficient POSIX accesses like you would prefer. So basically the POSIX API is just spending a lot of time waiting on inefficient accesses to complete. You can see that there's a decent amount of HDF5 time spent here too. I think that's just HDF5 spending a lot of processing time trying to generate the accesses that go through MPIO and POSIX. And you can see that as far as MPIO goes, it's basically negligible. In this case, you're using independent IO, so MPIO doesn't really do much. It's essentially just passing through the operations the HDF5 is generating to POSIX. So all kind of makes sense and speaks to a kind of inefficient independent file workload. On the other side, collective is much better behaved. You can barely even see HDF5 and POSIX contributions to the overhead. MPIO is definitely the more prominent of them. This makes sense because we're leaning heavily on the MPIO collective IO algorithm here. So it's spending a decent amount of time communicating results with other processes and things like that. But you can see, it's not a bad thing. It's a really good thing in this case. It's able to really kind of take the pressure off of the POSIX layer, and obviously it gives you a really big performance boost in this case. Now, just as an aside, I could have easily, misconfigured something here to lead to these, drastic results or something like that. But that's not really the point so much. It's just kind of making you guys aware of, what kind of analysis you could think about, or how you could kind of think about these performance issues before you start to kind of, try and tackle them. Using the same exact example, another thing I looked at was just a way for us to kind of reason about how this HDF5 application dataset accesses correspond to chunking parameters users are using. In this example, there actually isn't any chunking enabled, but this is just kind of what I imagined we could use this sort of information for. We're basically capturing in these radar plots the dimensions of access that are commonly being used for this application. So starting on the left side is a radar plot for 2D accesses. So you can see that there's only 2 dimensions on this radar plot that are being accessed, and it shows you for 2 different configurations, how large the accesses were in each dimension, basically. Similarly, on the right side, for 3D, there's 3 spines that are active here, and shows you basically what for the most common access sizes, how much data in each dimension was being accessed. So if you had some similar plot for what the chunking settings are for a particular data set, and you can compare these accesses to what the chunking parameters are to get an idea of whether chunk settings are kind of in line with the way that the data set's being accessed, which we think will be a crucial component to chunked data set IO. Okay, and I'll just kind of summarize some of the IO tuning options, since we've kind of covered a lot of different interfaces and some different tuning vectors in this talk so far. I just wanted to kind of zoom out and give you guys an idea of what you kind of have available to you depending on what you're using. So striping is easy. We kind of saw earlier that it's basically just a command you issue on the command line to the file system to set striping parameters. So it's really, applicable to basically all of the different interfaces. So whether you're using POSIX at the lowest layer possible, or whether you're using HDF5, it's definitely important for you to consider striping. On the alignment front, It's a little more complicated. HDF5 and PNet CDF, MPIO, they're all basically alignment aware. I have a check minus for POSIX because while technically you can, manually make sure you align your accesses via POSIX, it requires a lot of work on you as a developer to do so. Whereas the other examples, it's much more automatic. It's kind of just like HDF5, for instance. If you set an alignment value, then it'll honor that and make sure it's generating IO requests that are aligned, which is a lot more convenient than manually doing that yourself. As we've seen, collective IO is really useful. It's obviously available in MPIO and also used by both PNet CDF and collective IO to give you really performant IO to shared files. And lastly, chunking is something that's only applicable to HDF5, but we've seen how it can be a really useful optimization if you really want to make sure that your file access patterns kind of match how the file is organized on disk. Just generally speaking, I think we would suggest users to try and use high-level IO libraries as much as possible, where possible. Collective IO and chunking, as we've seen in the previous examples, can give you really large performance gains, and they do so with kind of minimal effort on your part. There might be a little bit of research on your part to find out how to set those particular settings, but you're obviously not having to go through the complete engineering task of writing those things, which is great. Okay, so next we'll talk a little bit how to adapt to technological shifts. So we've covered, again, a lot of technologies today, most of which have been, or most of our time is being spent on things that I would consider very much traditional HPC, MPIO stack, things like that, MPI programs. And that kind of stuff's been deployed at HPC facilities for decades now, and we're all, pretty comfortable working with it. But, as we're, probably aware, and I think some of the presentations today have touched on this, the landscape's constantly changing. So there's not only, at the top of the stack, there's, new computing paradigms. Not everyone's just using MPI, large scale MPI programs for science. There's all kinds of new, frameworks out that people are interested in using. And at the bottom of the stack, you have emerging storage technologies. So it's not all spinning disk at the bottom anymore. There's different hardware technologies, and they're located at different locations throughout the computer now. So there's just a lot of different things that could change as far as that goes. So one thing, I guess one way to handle that with Darshan is, or I guess, let's see. Yeah, just as I guess an example of different non-MPI frameworks, which we keep hearing a lot about, particularly and on the Darshan front, we've heard a lot from people that are interested in machine learning and deep learning recently, which is kind of a challenging workload to get right. It's obviously not using MPI, but we've observed that there tends to be a lot of files accessed in these types of workloads and stuff like that, which is challenging for Darshan, coming from the traditional MPI applications that don't necessarily access as many. There's also just other kind of data analytics frameworks that folks are interested in using, like Spark and Dask. And there's also, other non-MPI distributed computing frameworks that folks use, like Legion and UPC. So we've had, a lot of desire on the Darshan front to better accommodate, changes like this. And as I mentioned earlier today, we've traditionally just been tied to MPI. So this is something that we wanted to address. So starting with Darshan version 3.2.0, we can instrument non-MPI applications. So we no longer, require users to have to call MPI init or MPI finalize, so they can basically use this non-MPI version of Darshan for any other type of serial program or some, issued by something like Spark or Dask or what have you. All that you have to do is set the Darshan enable non-MPI environment variable, and it should just basically work for you. And in this case, it will generate, again, a unique Darshan log for every process that's invoked while you've got Darshan enabled like that. I guess one thing to mention here is that applications must be dynamically linked to use the non-MPI version of Darshan. So if that's not the case, then there's not really a whole lot that Darshan can do for you. But I think most of the examples I've looked at in this space are using shared libraries, obviously. So we're excited to extend Darshan into this new context so we can instrument Python frameworks. Like I was mentioning, we're very much interested in being useful to things like PyTorch and so on. We can use Darshan to instrument file transfer utilities. So any of the utilities used to copy data to and from compute nodes, whether it be SCP or BBCP or Clovis or whatever it is you're using, it might be also useful to kind of have Darshan characterize that type of stuff. Also, data service daemons. So not everything's necessarily a file system anymore. So you could have data services that are spun up, co-located on the compute nodes with your applications. In which case you might be interested to understand how they interact with the storage resources available to them, and basically any other serial application. So again, this is something that's kind of new for Darshan, but we're hopeful that it'll be useful to a lot of users that aren't necessarily married to MPI anymore. So moving to the bottom of the IO stack, we've heard a lot about parallel file systems today. And as I just mentioned, there's also this, things like storage services and data services are becoming more popular as they're not as, monolithic and hard to get good performance out of as parallel file systems. So, we've heard about new technologies like burst buffers and NVM and things like that today. And so basically, we're just trying to come up with new storage services that are able to better access those devices and expose them to users, basically. So some examples would be like things like Unify and Deos that have come out today. So one challenge with Darshan is how to properly, instrument new services like Deos and things like that. So one of the things with Deos is that it's not a file-based, storage system. It's using objects. So that's something that Darshan's not, doesn't have to necessarily deal with in other interfaces, but something that we're trying to think more about how to extend Darshan to different non-parallel file system use cases. So I think you can basically, the takeaway from the last couple of slides is that we're very much thinking about, both ends of the stack and how Darshan kind of fits in and can continue to enable, IO insights, as things continue to change. How am I doing on time? 15 minutes, okay. I think I just have a few, yeah, okay. So one other thing I want to mention is something that's relatively new in the Darshan field, something called PyDarshan. So this is a Python interface to Darshan log files that we're hopeful will lead to a lot more straightforward analysis of Darshan logs. So as we kind of covered this morning, most of the traditional analysis utilities for Darshan are based off the C Darshan util library. So you have the Darshan job summary, which we spent a lot of time covering, which is kind of static. There's not really much in the way for users to customize that and so forth. You kind of just get a report and that's that. On the other side, there's the Darshan parser, which is able to dump out everything in a Darshan log file, but it's really kind of overwhelming for users to try and take any insights away from just a raw text dump of all these stats to different files. So one problem we've also observed is that there's not really any other kind of mechanism for users to write their own analysis utilities other than writing C programs. And no one wants to write an analysis program really in C unless it's really simple. And then also users could also just parse the output from Darshan parser's text output. That's really kind of expensive to dig through all the text and look for the data you're looking for, depending on the size of the log file. And it's obviously not a fun exercise in coding to kind of write your own code for extracting relevant counters and whatnot. So it's not really really the best for that. So we've written PyDarshan, and shout out to Jacob Lukow at DKRZ for doing the lion's share of this work. But basically, it's some Python bindings to our C-level library, also with some higher level interfaces that kind of expose Darshan log data to you in like a format you would expect in Python. So you can get dictionaries or pandas data frames or NumPy arrays that contain all the different counters for different files that Darshan has information on. And this is something we're kind of investigating now and starting to see, how much simpler it makes the process of designing new analysis utilities. But it's something we're hopeful will kind of get users more excited and more willing to come up with their own kind of custom analysis stuff, whereas in the past that was just a lot of tedious work. So one thing we've already kind of been using PyDarshan for is using Jupyter notebooks as kind of ways to share information with users and collaborators and things like that. So this is just kind of like a quick example of how you can get read a Darshan log into memory via Python and start using some simple plotting stuff or whatnot to come up with your own kind of analysis stuff. So in this example, you can see just the very little amount of code it takes to get this stuff. So you can import a Darshan module and then create a report based off of a given log file name. And then this report.info call will give you all kinds of details about the job. And then over here on the right side, you can see you can plot it in Access histogram and give it a particular module. Like in this case, we pass in POSIX. And it just kind of really shows you how straightforward it is to generate your own graphs or do your own analysis as compared to what we had been doing traditionally, which is great. So if this is something you're interested in, we have some examples, notebooks, and things like that in our PyDarshan directory in the Darshan repo, which you could have a look at if you're interested. PyDarshan itself is available on PyPy now, so it should be really straightforward for folks to go out and install. So you could just do pip install Darshan from your laptop, and that'll give you a PyDarshan module that you can then import and start tinkering around with analyzing log files via that. So again, if you find you've exhausted all the information you can extract from the Darshan job summary and you don't have the stomach to look through Darshan parser output, then maybe this is something that you'd be interested in to tinker around and try and see if you can learn more about your application IO. Okay, and I think I've got a little more bonus material I can work through. I know I'm 10 minutes early. I'll go ahead and wrap up and then maybe open it up for questions. And if folks have some, then we can talk about that. And if not, I can kind of talk through a few more slides if there's nothing else we want to talk about. But just kind of to conclude, so we've covered a lot today, but I'm hopeful that this presentation in particular is really useful for helping you tie things together and get started thinking about not only how to understand your IO workloads, but how you can think about potential tuning vectors that you have available to you. And again, two of the things I've tried to keep hitting at is, there's optimizing your IO workloads isn't necessarily a fun task, and it can be challenging. But hopefully, we've illustrated that there are definitely performance gains that you can take advantage of if you're willing to put forth the time and effort. And also, don't always count on the different libraries or file systems to automatically do what's best for you out of the box. It's a very optimistic way of thinking about it, and I'm sure that the file systems and IO libraries would be happy to disappoint you. So yeah, I'm hopeful that we've given you enough details on Darshan to give you some tools to start investigating some of this stuff. I've got the Darshan GitHub page here if you're interested in downloading or installing or having a look at documentation or anything like that. But obviously, please feel free to reach out to us instructors here, or if you have questions about Darshan in particular, we have a Darshan users mailing list, or you can ask open issues on our GitHub, things like that. And obviously, the facility staff is also a great resource for you guys. So don't forget about them either. But yeah, hopefully this has been helpful, and I'd be happy to open it up for a few questions. And if not, I've got a couple more slides I can talk to.
Yeah, we did have some questions on Slack, but I think they were mostly kind of technical stuff we could answer in line.
Okay.
I think the main theme from the Slack discussion, though, seems to be that your talk, showing some of the different tuning considerations, called out, sort of provided more concrete examples of some of the things we talked about earlier in the day. So maybe we need to think about in future sessions having these sessions closer together so that we can, highlight with these case studies the things we're talking about in a more abstract sense earlier.
Yeah, no, I think that makes sense too. We kind of taken a save the tuning for last approach, and maybe it makes sense to kind of do the deep dives right alongside the original presentations.
But I think this material is great, and I think it seemed like we got a lot of other people on Slack very interested in understanding more about it. So.
I guess I got 8 minutes left. I can kind of quickly step through some slides that I talked through in this talk last year, and I wasn't sure because I squeezed in more material whether I'd have time to get to it. But I can step through it real quick just to kind of give you idea of other things you can think about for understanding and tuning HPC I/O.
And Shane, before you, after you do this, make sure you remind everybody to stick around for a group screenshot.
Right.
Photo.
That's right. Get your cameras ready for the 70-person group shot. Okay, so one thing I wanted to talk about is a project that we've worked on in the past that kind of tries to extend this understanding I/O beyond the application. So what we've talked about with Darshan, it's an application-oriented I/O analysis tool. So it tells you about all of the libraries and whatnot that the application is using, but it kind of ignores broader system-wide information, which is important because HPC facilities are shared between users. So it's not just your application that's accessing different storage resources and things like that. So a system level perspective is really useful for kind of contextualizing your application I/O performance. There's a lot of different existing tools that are able to capture information about different levels of the I/O stack. So again, Darshan on the application side, but there's also things like IPM and Recorder and so on that capture MPI communication details. So you can kind of think about them as being Darshan, but for communication as opposed to I/O, which is definitely important. There's information, or I guess there's file system monitoring. So there's this tool called LMT, Lustre monitoring tool, that can give you monitoring information on a Lustre storage server basis. And there's underlying IO stat and things like that can give you lower level details on storage arrays and so on. So there's a ton of different tools that might be available on different facilities as far as capturing information about what's going on from an IO perspective, not only on compute nodes but across the system. So this project I mentioned is called the Tokyo project, and was used to kind of provide a framework for holistic characterization of HPC I/O workloads. So the idea was to kind of collect, integrate, and analyze this disparate I/O data from all these different contexts and use it to try and make insights into general I/O behavior on HPC systems. Was also meant to kind of come up with a platform independent blueprint for deploying and utilizing I/O characterization tools, data collection, storage services, and things like that. And also just to provide a lot of relevant data for characterizing HPC IO workloads that could be used for, research or for facilities folks or just interested users and so on and so forth. One of the utilities that we were able to come up with out of this project was something called UMAMI, which stood for Unified Metrics and Measurements Interface. It was basically just a way we came up with to contextualize application performance with other system measurements that we were able to get access to. So you can see here on the right side, we have these UMAMI graphs, and basically they're just to kind of plot different metrics of interest over time as a user is submitting, similar jobs. So you can imagine, you run this same job regularly as part of a campaign or something, and you just want to keep track of what different metrics of interest are doing over time. And in this case, on the right side, you can see, the different panes going from top to bottom, showing the metrics, and then on the x-axis is time, and we just have points representing the attained performance metric over time. And you can see at the very far right side, there's distributions that kind of give you an idea for where the measurements kind of for the whole time frame lie at versus where the most recent run is. And the idea is basically just to be able to correlate, different performance parameters and to see how they're changing over time to see if we could observe anything interesting. So yeah, just kind of quickly walk through some of the things we captured. So at the very top is raw performance of the IO for an application. So you can see in the example here that IO is not awful, over time. There's a little bit of variance, which you would expect, but all kind of within the range distribution there. And then the last measurement just completely fell off a cliff. The coverage factors, those are metrics that kind of represent how much contention an application is I guess, causing. So it's basically comparing how much application IO was issued by this particular application versus how much was issued globally for the entire system. So if you had a coverage factor of 1, that would mean that you represent all of the global system traffic. And as you get lower and lower, it just means that the contention is higher and higher. And then there's also like metadata loads as measured at Lustre file servers. So you can see the average metadata server CPU load. You can see that spiked up really high in this particular example. And you can also see that there's a ton of like open close operations issued at metadata servers, which are definitely anomalous compared to past runs. But they just, in this case, we can't say for sure, obviously it would take a little bit more, deeper dive investigation, but we can see what types of things we could correlate against for performance. In this case, it seems completely reasonable to see the low performance, see the low coverage factor, which means that other people are running while we are, and then also see the high metadata server load. It's also impacting performance, but it's just kind of an example of some things we've investigated that kind of extend beyond the application and kind of start to consider more system-wide IO details. That's actually it for me. I think that's, yep, 3:15, perfect timing. So I'll go ahead and stop the screen share.